Western technologies behind that. So it is mostly IP based, so we understand it. It's not some circuit switch network where nobody understands how it works. So it's IP. And hackers understand IP. And so we took a look of that. And there are some very interesting features called self-organizing networks. So it's automatically done everything there. So there are a lot of procedures which may sound very curious, and we analyze it here. Because every good talk needs a message behind that, we've chosen the name LTE versus Darwin, and why we've chosen Darwin, why we will explain.
Okay, rather easy. Talking about evolution, of course, Darwin might be a proper enemy. And for us it's quite simple. It doesn't really matter if you care about Darwin or what he said or what he worked out. But in the end, there's one very little fact that's simply true about everything that you wrote. There are certain stupid things that you only do once. So, for a human being, come on, if you die, you're gone. And it's actually the same with, say, larger companies. We actually kind of hope that certain companies, if they do something really stupid, that they run out of business. So I know it's for our own protection that at least a few stupid things vanish and the world gets a little bit safer. So for us, Darwin was the main topic for this talk. The Darwin Award just as basis, I guess quite a few of you probably have heard of it. Created in around about 1985 in the USAID group. And the special thing about the Darwin Award is the stuff really sounds stupid. And you simply stand to read something like that about a guy accidentally sitting on a firecracker and taking himself out of, the duck line by losing his balls. You read stuff like that and you think, come on, nobody do that. Then you go to YouTube, have a proper look, and you actually find out that there are people who really do that stupid shit. Come on. You guys probably know security, and there simply are people doing that stupid stuff in the real world. So, for us the question is, the guys behind LTE, have they done the same stupid stuff or not? And with that, we'll start with a few basics from Henry, just to give you an overview of the whole system and everything behind it.
Okay, debaters. There are a lot of standards dealing with the application. If you are talking about 4G networks or LTE networks, there is mainly the 3GPP project, the third generation partnership project, it's called. All specifications there can be downloaded on 3gpp.org, so they are open, and you see how the functions are implemented or will be implemented by the vendor. Some more information you will get on ITU or from ETSI. So, if you're interested, just take a look, but the standards sometimes seem very, very complicated, but now we took a lot of them, analyzed them, and the most interesting stuff we put it in this talk. Then the architecture, how telecommunication networks usually work. For 2G and 3G networks, so GSM and UTS networks, for example, they're usually circuit switch domains. I will not explain that here. The most interesting part for us really is that the LTE networks are based on IP networks. So you have a packet core domain, it's called packet core domain. So you have IP packets. Everything there is IP based. And therefore understandable for everyone. And not only for some crazy guys or mechanics which implemented that stuff. So we are aware of this technology. Here is a typical weapon architecture of 4G networks. On the first view, it seems a bit complicated. I'm just explaining some basics now. Very important is that it's backwards compatible. So a 4G network is also supporting UTS and GSM. And that is shown here. On the left side, it's called access network. That's the radio network behind it. We have the UTRAN, the GRAN. UTRAN is for UTS networks. GRAN is for GSM networks. And then in 4G, it's called 4G RAN. So RAN for Radio Access Network. And the antenna is called eNodeB. It's one of the main components then. And there are several kinds of antennas we will explain later. Then we have the core network and some IP services on the network of the provider. The core network mainly has two devices implemented. There are two devices which are necessary for the functions. The first one is called MME, the management entity. And the management entity is responsible for controlling all the traffic, all the stuff which is happening there. So if you are dialing in, you are talking with the MME, and the MME says, yes, you are allowed to get in or not. And then you have the SAD gateway, or PDN gateway, there are several names for that. PDN gateway is the most important one, so it's a packet data network gateway. It's just an IP gateway which is routing your traffic from somewhere to somewhere. So, and then you have a lot of gateways which are dealing with that, like serving gateway and so on. Not interesting enough, not really interesting now. And some more components like databases and so on and so on. So, get back to our talk, to our analysis. We start with the most obvious one, the mobile phone. So what we really see as users for the network.
So the first part actually is, as Henrik already said, the eNodeB, the antenna part. So the eNodeB is the logical unit somewhere in the field, connected to the backend via, well, LAN, normal networking, and on the other hand, simply connected to the antenna. Now these boxes actually come in different sizes. You've got a few, well, eNodeBs that are, say, size of a normal 19-inch rack, but you've also got some that go down to the size of a backpack. While doing our research and while trying to acquire an eNodeB, we actually found a Chinese company who wanted to sell us a fully battery-powered eNodeB. So, for using it on the go and stuff like that. Then you've got the different cell sizes. Now the macro cell is kind of the normal cell size that you know from a GSM network. Then you've got the micro cells, around about 100 meters less, which you'd have, say, on rather large company premises. Then you've got the pico cells, which you'd have in the building complex. Or you've got the home eNodeBs, which are actually intended to use for private units or for small office units. So that's exactly the same as the classical femto cells that have already been on the market for a few years. Now the interesting part is, of course, eNodeB is termination point for encryption. So most encryption channels, say from your mobile phone to the LTE backend, aren't encrypted in one go. So you've got one encryption channel to the antenna and then a second encryption channel into the backend. So attacking one of those eNodeBs really is interesting, because you'd be able to fetch quite a lot of information just from that single spot. Now, as I said, the different kinds of cell sizes, they make the whole LTE network more complicated than the GSM network. You can see on the left picture, you've got a small town, you have two very simple GSM antennas. Now in the LTE network, you've got stacks of smaller and larger cells throughout the whole town. And the LTE specification actually also includes technology like Wi-Fi or WiMAX. So in theory, it would be possible that your mobile phone, when you say go into your building, routes from the LTE network into your simple Wi-Fi network. And when the whole standard is really implemented, then even your phone calls, which would go over voice over IP, would move from the cell network down to a Wi-Fi network, which of course gives us quite a few more interesting attack vectors, and especially very easy attack vectors. Now another very important aspect is the fact that, say, in GSM networks you've got one cell mask, you've got one cell. In LTE you've got the cell mask with directional antennas. So say you've got 4 antennas showing to all 4 directions, all of these antennas can actually open a different cell. So if you go around the whole cell mask, you really move through different cells while you go around. And another important thing is that the E node B, say, if you want to attack it, has to be placed rather close to the antenna. So if you've got a passive antenna, then the distance between the E node B and the antenna is only, say, well, 5 to 10 meters. So really on the foot of a cell mask or on top. If you use an active antenna, which are the ones that you've usually got on larger buildings, so if you've got something like a small rack in the cellar and an antenna on the roof, then you've usually got a fiber connection in between, which gives you a little bit more flexibility. And then, as I said, as Henrik also said, the fact that it's connected via LAN. We've been using that technology for quite a few years. We've been attacking it for a very long time and very efficiently. So, if you actually manage to get into that network, you'd be able to use the same attack methods that we're usually using in very normal networks. Now, the next aspect, the UE. Well, the UE is simply user equipment, which is, well, mobile phones, whatever 4G sticks, tablet PCs, and everything that you got. And usually if you look at stuff like that, you actually want to detect the device itself. But for us, the main question at the moment is, because LTE is new, we've got to do reconnaissance, we've got to learn. We actually want to know what does the device itself know? What information can we gather by using a simple, normal mobile phone? And if you have a closer look, the typical aspects that you find are the cell ID, or the physical cell ID, simply a 3-digit number, the cell that you're in. Then you've got the tracking area code. The tracking area consists of multiple cells, which is something new in LTE in that form, and we'll talk about that a little bit later. Then of course we've got the signal strength and the position. Now, the physical cell ID is made in such a way that we've only got 504 different cell IDs. So you've got a dynamic network, and the only aim is that no two adjacent cells have got the same ID. So it could be possible that you move from cell 1 into cell 5 into cell 1. But the first cell 1 and the second cell 1 are two different cells. So yet again, it's getting more complex. And for that, the LTE specs simply give you the aspect of self-organization and self-configuration, which will come up a little bit later. Now, the tracking area code is interesting because that's the smallest collision domain available. While before the GSM, if a phone call came in, every mobile phone in that cell got a message, a simple wake-up message. Nowadays in LTE, every phone in a tracking area gets this wake-up message. So for us, the question is, how large are these tracking areas in reality? Say, would I be able, when standing here, to actually find out that somebody on the other side of some phone is actually getting a phone call at the moment? Or if I can only notice for the people in, say, a range of 100 or 200 meters. Then, well, signal strength, rather normal, and then the location. Now, the LTE specs have actually added a few new nifty functionalities. So if your mobile phone wants to know where exactly it is, there's the ESMLC in the backend, which simply helps the mobile phone. So the mobile phone sends a request to the cell mask, saying, hey man, I want to know where I am. Then the cell mask processes it, forwards the request to the backend, and the backend will actually work out the exact location of the mobile phone. Simple triangulation, things like that. So LTE has actually implemented those aspects for you to use, which is, well, makes life easier. So now to access that data, you can use the famous magic numbers. So on the iPhone, if you press star 3 or 1 and the rest, then you get a whole set of information screens. So giving you the physical cell ID and aspects like that. On Android, well, the other order. The thing is, why do we need all this information? As I said, LTE is new. We need to understand the network to be able to say if it's safe or not, to be able to say if it's attackable or not. So, as the same thing as in Wi-Fi days, we've got to start doing more driving, we've got to start collecting information, which is partially actually what we're working on at the moment. So what we did is we wrote a small application for Android, which will be released in the next few weeks, that rather simply accesses information on the Android phone. The device doesn't have to be rooted for it, it just has to be rather new. I think you need the Google API version 90. And then you can simply start reading out the set ID, the physical set ID, use location data, and what this application simply does is, all of it is simply dumped into a text file. And what we're currently working on is plotting all this information into a map, so that in the end we've made, hopefully got a map, say, of large cities, where we know how large is each cell, how large are the tracking areas, where exactly are the cell masts. So simple reconnaissance work. And this actually is the aspect where we need your help. As I said, we're going to publish the app in a few weeks, and it would just be great to have a few people around the world using the app, collecting some data and sending it to us. Just that we actually see the whole worldwide deployment of LTE, and that we actually can try to document structures and simply work out what attacks would be feasible and what wouldn't. So, then you've got the other side, third-party awareness. Who sees me in the network? Who knows that I'm there? It's an IP network, so you can simply, if you've got the mobile phone or LTE, you can start the normal nmap scan and find all other mobile phones in your address space. Some providers have got measures against that, some don't. So, yeah, your mobile phones might just be as attackable as your normal computer with a public IP address, even though it doesn't really have any security features on it. So one of the really funny aspects in that case is something like, say, the worms that use rooted iOS phones. You've got the OpenSSH ports, and in those days this worm only used Wi-Fi. Say in LTE networks, it could actually simply move through the whole internet. Finding out Wi-Fi in its own address space, attack it, and move on. So those are just things that we have to keep in mind in the future. Then, just as a small example, the attach procedure has been rather interesting in the past few years, especially in GSM and UMTS times, working out where encryption has been put in place, what security measures we've got. And we actually thought about taking this part out of the talk, but there's one simple aspect why we really need it. So we've got a communication relay from the node B to MME in NAS messages or control messages in the backend, going from the node B in the field into the backend, is, as the specs say, always encrypted. Those are the specs. Then you read it a little bit further, and you've got 3 different encryption algorithms. So I guess the nice ciphering algorithm is probably the strongest encryption that they've got in place. And most probably, quite a few providers will simply have used exactly that algorithm because it's easy. They've got to put up the network in a very short time. If you use encryption, something will break. It doesn't mean that you've done something wrong, but encryption simply means stuff breaks while you try to implement it. So, simple solution, don't use encryption, and in the end you don't have to switch it on because yet again you might break something. So from our experience, if you really look at telecommunication networks, you will find unencrypted communication in the field. So say you open a switch box, plug in your own laptop, and you see LTE communication on the cable in Wireshark. Not nice, but that's simply the way it is. So, next interesting aspect is paging. Now there have been a few attacks on paging in GSM. So, a paging message simply is a wake-up call. Your mobile phone, as you've got in your pockets at the moment, is in standby mode. So, it doesn't have to communicate with the internet or with the cell master the whole time. It simply waits until a call comes in. So this paging message is simply a hey phone, wake up. Then the phone will contact the backend and say, hey, I'm here, what's up? And the backend will tell the phone, here, there's a text message for you. Now, in GSM networks, the whole thing went a little bit wrong. So if your mobile phone got a message, there's a new text message for you, some other mobile phone might have just had the chance to simply say, I'm the right phone. So text messages and phone calls would have been relayed to the wrong device, and we'd have a whole DOS state. So for us the question was, is the same possible in LTE? And sadly enough it isn't. So in LTE networks you've got frames that are sent out from the cell mast all the time. And the frames consist of simple binary digits, and every mobile phone only looks at one single digit. There's stacks of maths behind it. You've got constants from the mobile phone, you've got constants from the cell mast, so that your mobile phone knows which bit is your own wake-up bit. In the end, it works out that you've got 32,640 different wake-up bits. So in the end, you can only contact that amount of devices in one single tracking area. In the end, it might be possible that you've got more devices in the tracking area, which means that when a page goes out, more than one device would wake up and say, hey, I'm here, what's up? So of course, only one of the devices would get a reply, but the other one would simply come up. We thought about the attack, we had a closer look, we actually tried to work out a way to use it, but in the end, the only way that we worked out was to, search some battery power of devices, but that's come on play. Then we had another small idea, actually by accident while having lunch, because Henrik sent me a text message, I saw it and I noticed that I had a fallback. So in LTE, in theory, voice communication is supposed to be voice over IP, and the same text messages are supposed to be SIP messages. That stuff isn't really implemented yet. So what do the telephone provider or the cell providers do? They give you a fallback. So your mobile phone is in the LTE network, and then simply drops down to GSM or to UMTS for the phone call. Which in the end can actually be rather interesting. Because say you've got some dedicated device somewhere out in the field using LTE to go into your corporate network. If I had the phone number of that device, and I call it, and put my phone down again, and call it, and put my phone down again, your dedicated device wouldn't stay in the LTE network. It would always drop down back to GSM or down to UMTS, which of course in certain situations, depending on what the device is on the other end, really can be critical. Well, we haven't really found any dedicated devices yet that we could try it on, but that's just one of our future parts. And after looking at the front end, we'll just jump over back to Henrik and have a close look at the back end.
Yeah, so that's the radio stuff we've not seen. We are still researching on. We have some more interesting stuff for the backend structure. So, but it's always complicated to get into it. So here's like what I've explained before. A breakdown structure. So we have some very interesting components. We have the antennas, we have the management servers, and we have gateways there. And in the back end, we have databases where all the user data is stored there. And now the question is how to get access to the back end network, so the transport network and the core network. As an attacker, it's really interesting. So if you're in the network, probably you might do a lot of damage. And here is a picture of a typical antenna station somewhere out in the field. How do people may get access to that? Just look at the picture, so, or even this one. So the components are just staying somewhere around. This is close to our home, for example. So the security mechanism you see here, the cables are just here. This is an Ethernet cable here coming out, for example. So you just have to plug in and then you are in the network. So sometimes it might be more easy than you expect. But yeah, sure, you would believe in that providers have some security mechanisms against that. Even there are specifications. So in the standards, exactly in 3GPP, TS 33403, they're standing. Bees, so the antennas, shall be authenticated and authorized. Yeah, that's what the standard says. And now is what we've seen, just some pictures. Here, for example, like Brian explained, you can do just a internet scan if you're in the network because there's all IP behind. And if you have access to the antennas, so if there's a filtering problem, for example, in the antennas in the provider's network, you might get access to an ENOB. ENOB has an IP address. Yeah, and here, for example, is one outcome. So it's Telnet, very secured for authentication. I connected to, and you see, here's a banner called ATP CLI. ATP CLI is it's a client interface for base station. So it's a Huawei base station I found here. So, and it's using Telnet. That's not secure. Another point is, for example, on some tests we've done, we tested some database, so it's called Home Subscriber System, HSS. That's the stuff where your user data is stored in, so that's are the balls of the provider's network. And there often are all protocols used for management, like LSH or rsync and so on, or even Telnet again, and without authentication. So here, for example, we figured out that we can get access via RSH, and even then we had a root shell, so that's not authenticated, that's not secure. So, and this is really, really dangerous. So if there is no filtering in the network and you have direct access to those components, you might get access. Why is it so? It's because those components are very old, so they are about 10 or 20 years old. They're just working. They are on the network and they're working, and nobody cared about security. So standards say authenticated, but in reality it's not like that. Even if there is filtering, there are some points, some information which makes filtering very complicated. So in your mobile phone, if you connect to the network, if you are dialing in, you have to use a so-called access point name. The access point name just describes the gateway you are using, and you can modify that. So often there are access point names just for debugging or for testing services. Just use test as name, for example, and sometimes you'll come in. The common access point name is internet, but that's what usually people use, but hackers might use some other, like management or something like that. And then you will get into another part of the network of the provider. So we've written a small tool to do that, so it's called APNDF. So it's a small brute forcer. If you're interested in, want to look at it, just take a look here in this link. You can download it, it's open source. And it's really interesting to play around with that. So sometimes you might find very interesting API names. Okay, what are the standards saying about security? All the security in 4G networks are mainly based on IPsec. And everybody of us knows how good IPsec always is working on. So there is standing for the interfaces. So from the ENOB to the backend, the interface is called S1 interface. And there are control interfaces between ENOBs, two ENOBs too. This interface is called X2. And for both interfaces, for the control traffic and for the user traffic, so your ports, it is required to implement IPsec. Again, that is what the standard says. And often for IPsec, then security gateways are used. But, and here's another note from the specifications. In case the control plane interfaces are trusted, for example, physically protected, there is no need to use protection. So, and this note most of the providers noticed too, and so they are not implementing IPsec everywhere. That is for every control and user interface. And again, back to our picture, is this physically protected? The provider might say yes, because there's a fence and some blocks out there. But for me, as an attacker, no, it's not physically protected. So you can, so I would say, often, if you would plug in here, you will not see encrypted traffic. That is what reality really saying. And if you have access to this network, to the interface, then you can participate in the control network. There are mainly 2 or 3 protocols used there. They are specially developed for telecommunications. One control protocol is called GTP, GPS Tunneling Protocol. It's more used in the backend. We had a talk some years ago on Schmidt, where we demonstrated that we can inject every message, because for that protocol, it's really old, there is no authentication. Everybody can inject traffic and do some control stuff. For 4G networks, they developed some new protocols I will show you later. And these protocols are used for the interface from ENOP to the MME, or from MME to the gateway, just to open sessions and so on, to transport the control information, the configuration data. And this traffic usually for the IPsec. But that's not even everything you can do as attacker. There are even more interesting protocols used or control traffic you will find. Often DHCP is used to, if you are plugging in a new ENOP as provider, often the first IP address is provided via DHCP. So an attacker might have this too. And there are a lot of more services you might attack. DOS protocols information, and there are CMDBs you might attack. You have the typical certificate problems, and a lot. You have management interfaces like I've shown, so there are really a lot of possibilities to do. And now, again, that's what our providers doing. That's a good point, a good development, but it's really late because the new standard is just from last year, and it's still a bit in development. It's called SECA, Security Assurance Methodology, and that says that providers and vendors have to do pen tests, and that's actually good. So for security, it's really good. So they are testing if they are secure, and exactly such problems like we've shown here in some pictures can be fixed then with this methodology, with this process behind that. But now we want to be some more technical, and we want to show you what we've done, and sometimes it's too easy. And therefore we will focus on the S1 interface, so that's the 4G control plane interface. So that's where all the dialing in information is transported over, and where the authentication data is transported, and so on and so on. This interface we focus now on, and there is used a protocol called S1AP. For S1AP, it stands for S1 Application Protocol, so somebody invented a very nice name for that. So S1 is interface with an application protocol, very nice. And it's using STP port 36412. And we wrote some tools to test implementations, to inject traffic, to spoof messages, with our own toolkit called Dizzy. I will show you later. It's just, we have written some tools to do that. If you're interested in here, you can go on that. And it's a new protocol, something developed that. And with all new developments, it's already dangerous. It might go in the wrong way, like maybe here. This should not happen, so somebody developed something which is wrong. Therefore it's new, and we took a look into that. One will now explain which procedures are behind that, why they developed that protocol and what it is able to do.
So, as I said, from the whole structure, LTE networks have gotten more complex, especially from the device side. And even without getting more complex, all the companies want to save money. So what's the main problem for a telecommunications company? They want to set up a new cell box. They've got to send out a highly trained technician that is able to configure a whole base station. So connected by a serial port or whatever, configure the local data, the position where the device is, program in what cell ID it's supposed to have, and configure the whole device by hand. Which of course means it costs a lot of money and it's complicated. So what do you want? You want the whole thing to get easier and simpler and quicker to set up. So as Henrik said, you don't want to use DHCP. You connect the eNode B to your normal telecommunications network, plug it in, the eNode B will get an IP address, will fetch a communication file, configuration file from some backend server, configure itself, and in theory it's ready to go. So even though all that makes stuff easier, hey, plug and play is simply a great idea. Doing it in a large-scale network like that, with that many different access points and access vectors, it's simply too easy to misuse it. So, of course, from the specs, there are certain, well, security measures. So, say you only get your configuration file if you've got the correct MAC address. So, kind of the few vendor bytes from the MAC address have to be correct. And you can look them up. Give your notebook a new MAC address, you connect to the network, and you get the whole eNode-based configuration file. Take it, go to the next one, you know what you're looking at, what you're waiting for. So, as good as all this stuff is, as much as it does make stuff easier, for an attacker it's simply just a large limitation. Even then, the whole configuration from the position where the device actually is placed, the technician doesn't have to do anything anymore. Most largely eNode Bs have got a GPS receiver in them, mainly for timing data, so simply get the time information from the satellites. On the other hand, they simply get their own position from that. So in theory, if you take down an eNode B, disconnect it, take it somewhere else, reconnect it, yet again the eNode B would see that it's got a new position and could actually change its own configuration and get new data from the backend to work on in the other place. Those things are quite interesting for, say, emergency networks. There are different structures that, after whatever large catastrophes, emergency services have to go in and set up a communication network. In those situations, great. But in a rather static network, it's just a large risk. And then you've got another very interesting part, which is the relay node. So the relay node is simply a repeater. And yet again, this repeater doesn't have to be configured. You place it somewhere, it will connect to the LTE network, just as a normal mobile phone does. We guess that it probably uses a highly secure APN, probably called something like configuration or setup. Connects to the backend, into the communication provider's backend, and gets its communication file, and then starts working. So, yet again, if the relay node is able to get that data, we might be able to do so. So, change the APN, connect to the network, say, hey, I'm a relay node, give me information. And even then, even if it's a stupid, complicated configuration file, it's part of reconnaissance. You can be sure that you learn more about the network structure from a simple file like that. So, yet again, another thing to look at. And then you've got the aspect self-optimization. So, self-configuration is the part from when you set up the network, or when you add a new component. The aspects of self-optimization actually mean that the network is able to change its own structures depending on the current situation in the field. So, yet again, talking about Darwin optimization. That's the way it goes. So, eNode Bs will work out the best configuration for themselves so that there's no overlap. Overlap meaning in time domain, in frequency domain, and also simply from the area, from the range of the radio signals. So, well, one eNode B might be able to contact another eNode B via cable. Doesn't work because only the eNode B itself really knows where it is. And then using geolocation data to find all the eNode Bs around himself is rather complicated. So, what did I do? Now, the eNode B will use your mobile phone. The eNode B will send a message to your mobile phone saying, hey, what cells can you currently see? And your mobile phone will answer, I can currently see your cell and 3 other cells. And will pass on the cell IDs. Then the eNode B will use these cell IDs, connect to the backend, say, hey, I've got the cell ID close to me, use the eNode B, we'll get an IP address, and we'll start a direct point-to-point communication between the 2 eNode Bs. Simple solution, but still the interesting part is your mobile phone was part of the communication. So for us nowadays, basebands are still magic, and they're still rather secure. It's still rather hard to actually get all this raw data out of a mobile phone. But in theory, if you could really do so, your mobile phone would tell the cell mast here in Sao Paulo that it can actually see a cell in Berlin. Of course, 2 different providers, it wouldn't work, but say very large differences in between. So one eNode B would think that it's close to another eNode B, a few hundred miles away from itself, and would start working out, well, sharing the time and the frequency domain with that other one to reduce overlap. So say you do that with one single eNode B and have 200,000 other eNode Bs just around it. It's self-optimizing. So that eNode B would say, hey, I'm useless. So it will reduce its radio power down to close to 0 and say, I'm in the way, the rest of the network may carry on to work. So yet again, you've got very interesting DOS attack vectors that might be used in the future. Now, what we're actually still waiting for is there's an LTE project for new radio, so using software-defined radio to well, take part in all the signaling. Sadly enough, the project isn't really very far yet, but as soon as that's done and people start playing with it, I guess LTE networks will really have a hard time. Then we've got, as I said, the communication. Every eNode B has got this name regulation table. So it's got a long list of all eNode Bs adjacent to it. And yeah, there are hard rules that the provider can add. Something like eNode B may not be move constrained. So have a static entry in that case. Or even blacklist other eNode Bs that the 2 eNode Bs may never communicate with each other. Yeah, that's the whole thing. So the name relation table is in the eNode B, and it's partially controlled from the backend. But yet again, the eNode Bs can partially work autonomous. So they do their own work. They decide what they want to do, and that's the way it works. Now, one very important aspect yet again is there are home eNode Bs, femtocells that could be in your very own house. And these home eNode Bs are made in such a way that they can actually take part in SON communication. So, say you've got this thing at home, I think the first femtocells that came up to the market were, I think, hacked in something like half a year. And people had access to the baseband and to the operating system. So let's say you've got your own home eNode B at home that starts talking to some cell mast and simply says, hey mate, I'm here too, I'm stronger than you. Come on, you just reduce at home. What does the cell mast do? Hey, it's the best way, the best thing for the network, so it reduces its output power. We do that a few times, And you might actually be able to switch off a whole cell mask without really needing any access to the backend or whatever, just by using your own home ENOD. Now, the idea is that in theory, the access from home ENODs is supposed to be protected by a so-called home ENOD gateway, which is a security appliance and, well, just a question of configuration. If the cells are really able to communicate with all large cells. But even then, say the telecommunication providers got their own home ENODs in the field. They might just be stupid enough to not make the difference between their own ones and your private ones. So yet again, another very interesting aspect for us to have a closer look at. So the LTE femto cells, or the home ENODs, are currently quite hard to get. I think there are something like 4 or 5 different ones on the market. And the Hitachi simply is just one example that we follow, just to have a closer look. Quite simply, being able to take part in the whole communication, the autonomous intercept, interference control. So even those specs say that the stupid box in your house will be able to have controlled access to the whole mobile phone network, which from my user view is great, from say the security view is awesome. So hey, just needs to misuse and really play with it. Then we've got the very interesting thing, the mobile traffic offloading. So say, depending on how your mobile phone provider or the communication provider sets up their own network, people passing by your house might be able to switch into your femto cell in your house. You know, the thing with your LAN cable on the side. Yet again, there are safe ways to do it and there are easy ways to do it. And experience simply says the easy way wins. Yeah, that was the other aspect. The voice over LTE. There are actually already a few projects that say that voice over LTE communication can roam into normal Wi-Fi networks. There are projects using that sort of techniques, in, for example, in our shopping malls. So if you've got your active mobile phone call over the cellular network, you go into the building and you switch down to their Wi-Fi network. So, yet again, you've seen the physical protection from the normal cell masts. How would you think the physical protection of the access points in a mall is? So the cell enough isn't one here right now, but screwed to the ceiling and 2 meters high with the LAN cable sticking out. Perfect. Just what I want, just what I can attack. And from that space, we're going to jump back to S1AP and have a closer look at the exact communication.
Yeah. So, what an attacker can do or might do, and how an attacker can do it, I wish I know. So we have seen a lot of ways to get access to the network, and now, yeah, what he might do or how he can do it. So there are 2 nice protocols, X2MP and S1MP. So X2 for X2 interface, S1 for S1 interface, but they are very equal. So that are those. That's the protocol used to do all that stuff. And if you have access to the backend network somewhere, you can send these messages and something happens with the management server or with ENODs in the network. So here is a list of messages which may be interesting. For example, there are positioning messages. So you can track other UEs, you can track your device, you can send authentication information, you can ask for authentication information in the backend, so in the databases. There are trace functions, there are reporting functions, logging information, or you even can hand over a call. So, for example, if you are traveling in a train or in a bus or whatever, you are changing the cells, and therefore there's a message to hand over your call from one cell to the other one. And there are control messages in place to do that. But there is one strange point that you are only allowed to send these messages if you are registered in the backend. Sure, of course, only InnoDs, which from that specific provider, should be allowed to do that. And therefore, there is a kind of automatically registration. It's called the setup request message. So the S1 setup procedure. New InnoDs will initially contact the MME and say, hey, here I'm a new InnoD from the provider. I have maybe some kind of authentication information, and give me my configuration and say what I have to do, what is my cell ID and how big is my cell, what's the tracking area, and so on. So the InnoD asks the MME what to do and give me some configuration or some stuff. If it's not working, that's very interesting. Here's from the standard. So if there is an unsuccessful operation, if there is an InnoD which is configured in one way, for example, he contacts MME, and then MME has to send failure information to the InnoD, so some kind of debug information. In practice, it's looking like that. So we did that just to test it and to do some kind of reconnaissance. And that is just one picture from Wireshark, how the answer may look like. And it's very, very informative for hackers. So the MME is sending the InnoD all the information the InnoD needs to participate in the control infrastructure. So they will give the attackers everything they need. The next part an attacker has to do is ask for configuration, or there is in the other direction the MME can push some new configuration to the InnoD. And again, more because there's the extra interfaces, this configuration can be duplicated between InnoDs. So there are three possibilities to distribute your own configuration in the network if you are participating as an attacker. And the most interesting one might be this one, because you can simulate an InnoD if you are plugged in somewhere at the field. So that sounds interesting, or not? And that's just one idea to change configuration of an InnoD. There are much more possibilities, like the handover or just a load invitation. One InnoD can say, hey, my cell, there are too much people inside, please I need a new cell just close to here to serve those guys. Or some other, you can trigger some operations like mentioned here for tracking, tracing, and so on and so on. Or even think there are roaming interfaces between providers. So if you are in the control structure, you might send control information to other providers and ask for some stuff, ask for user data, etc. So there are a lot of possibilities to do if an hacker has access to that network. To have a kind of proof of concept, we held a similar talk without that part here on the Schmidt, and we met a guy who wrote a tool called Marscan. Marscan is a very fast scanner for the internet. So it's scanning the whole internet for a specific port. And we implemented for us SST and scanned for the SST port for S1IP and S2IP. And there are a lot of interfaces open in the internet. Nobody will really do that, but there are some providers which have internet available SST port for control traffic of telecommunication networks. There is no need for, but it seems to be there, so that's really dangerous. And just a few thoughts what can be simulated with that. So there are open interfaces in the internet. You can send your own control traffic to. So you can plug in your own InnoD to that. Often there are MMEs staying in the internet, and you can plug in your own InnoD, and then you are part of the whole network. That's how it might look like. It's Wireshark capture, we, like I mentioned, we've written some very interesting tools to do that. So we injected some S1 IP traffic and it made it like this. And you see, we really have done it with some IP addresses there. There is a successful outcome. So that's an IP address connected to the other one, and I will not show here. And it really works. So this Wireshark capture shows that it's possible with our tools to connect to the control structure. So that's really dangerous. And to one of our colleagues, some thanks. So this is just some scripts with some framework we've written. Daniel, another guy working with us, wrote a tool called S1AP enum. And S1AP enum is using this failure information to connect to the network automatically. Just as a proof of concept that you see it's possible to connect to the infrastructure. It collects all information it gets from debug information, put it in the S1IP message, and then set us connection. And probably the only thing you really have to know is the so-called PLMN. And the PLMN is public available, there are lists for that. And with this list, you can brute force it. And then you get access to that. Here's a short screenshot of what the tool is looking like. If you're interested in, want some more information, visit our blog. The tool is open source. And here you see it's working with the tool. So here, the green one, I don't know if you can read it in the back, but there is a successful connect again to such a control network. Okay, so you see it's very dangerous and it's possible. Now we come to the end of our talk. So what is Darwin saying? Back to our message of the talk.
So yeah, in the end, the whole idea is very good, but it adds complexity. To yet again compensate the complexity, they add automation, which yet again kind of drops security a little bit further. So quite a few things, say some stuff like the null ciphering algorithm, or just the fact that in theory offense means don't use encryption is shocking. And well, we think they've learned. They've made it more secure than in GSM and more secure than in UMTS. They've seen that they had mistakes, they've seen that they've done stuff wrong, and they've improved. But in the end, it's still attackable. And for that, quite simply said, I guess it's down to you to decide how much you really like LTE networks and how much you trust them. Let's say stick to us in the future. We will carry on publishing information as it comes in and whatever our research shows. So let's say in future, have a close look at LTE and see how it goes. So as the final slide, the Random Darwin Award, even from Sao Paulo here, there are people doing stupid stuff. And telecommunication providers are really doing stacks of stupid stuff. Not because they are stupid, but because they use the easy way. And because they've got deadlines to hold, because they've really got hard stuff to do. So in the end, security would add complexity, so they want it. So the networks are nice, but they're still not perfect. But the future will show what comes and if LTE will survive or not. So, thanks a lot. If you've got any questions, just ask. Thank you.
Do we have time for questions? Other questions?
So you mentioned that the operator has the option to disable encryption altogether. Does that mean that the packets are in the clear over the air, or is it just one of the layers of encryption?
It's actually for the single communication channels. So we can activate IP set between a certain ENLP and a certain MAC component. So in the end, just because you find one ENLP with an encrypted channel, it doesn't mean that the next eNote is encrypted too. So it's really their choice for every single component to activate or not. So then, thanks a lot. Have a great evening.